Okay, there we go. Okay, again, sorry for the late start. So here we go. We were talking about planes in R3 last time, and we recognized that you can sort of analyze that in the same way that you do with lines in R2. Namely, there's a test for whether or not a point is on the plane. And it comes down to, well, is that difference vector parallel to the plane? And then you can kind of reason from there, same kind of reasoning that we did in the case of lines. And you get down to the equation of the plane. And then we talked about this example. It was the last thing that we did last time. Okay, so what we're going to do now is talk about different ways to describe these geometric objects. And let me just remind you, the first thing that we said in this discussion about lines and planes is we addressed the question of what is an equation. When we say we talk about the equation of a shape, the equation of a line, the equation of a plane, the equation of a parabola, whatever, what does that mean? Right? And what that means is we're talking about a test. If the test passes, the point is on the geometric object. If the test fails, right, then the point is not on the geometric object. Okay. So now I'm going to show you a different way to connect algebra and geometry in the context of these kinds of shapes. So I'm going to tell you something called a parameterization of a shape. Now, it's going to involve the equal sign and thus equations, kind of, sort of, but in a very different way. So as a result of this, I really don't like calling this the parametric equation, parametric equations of a line, or many other things we'll talk about. I rather the term parameterization because it doesn't have this awkward, inadvertent use of the term equation when this is not the equation of a shape. Right? So I feel like the term parameterization, by the way, is very standard. Does a better job of distinguishing this as a different way to write down algebra that in a different way connects to geometry. Right? Okay, so anyway, let's use this term parameterization. So here's the idea. Here's a line, and suppose what I know about that line is I know a point on the line, and I know a vector parallel to that line. Well, now I claim that that uniquely characterizes that line, right? There's only one line that goes through that point, and that's parallel to that vector. Okay. So with that being said, let me observe that every point on the line has the feature that it can be viewed as x naught plus some multiple of the v vector. Right. Okay. All right. Now here's this equal sign that I told you was going to be there, and so that's again, there's a temptation to call these. They are equations, right? But they're playing such a different role. This is not a test. This is not playing the role of testing points. You give me a point x, and I decide whether that is or is not on the line by, plug it in and see if it works. Because I don't know what that t might be. This is not a good way to test whether a point is on the line, right? So this is a different kind of a thing. This does not test whether points are on the line. This will generate the line. Give me any value of t you want, plug it in here, boom, out comes a point on the line. This is a point factory. This makes points. It doesn't test points, it makes points. Did you ever see the difference? Right? It's a different kind of a way of describing the line. So anyway, I think it's important to understand, see the different role that the algebra is playing here so you don't inadvertently conflate them. Now, how do you visualize this? How do you think about this? Very common choice to think of this t as being time. In fact, that's why we very often use the letter t as opposed to the letter q or m. Right? It's because we want to think of t as being time. So with t thought of as being time, notice what happens when you plug in. If you plug in t equals 0, that puts you at x naught. Right? If you plug in t equals 0, the resulting output is x naught. Likewise, when t is equal to 1, that puts you at this point that, is exactly 1v moved over along the line. Right? And keep going. When t is equal to 2, you're at that point. And so as time passes, as t increases, you move along the line. It's like you're tracing out the line. Everybody see what I'm talking about? Okay. Now, everybody knows there's different ways to draw a line. Here, I'm going to draw this same line here. I'm going to draw this line in two different ways. Here's the first way. Then I'm going to draw that line. Here's the second way. I'm going to draw that line. Right? Those were different. Right? So there's two ways to draw the line. Well, there's many ways. I've just showed you two different ways. Those correspond to different parameterizations. So you can start at different places. Right? These are two different points. I can move with different speeds. Here, look at this. That's my v vector that represents effectively your velocity as you go along. That is doesn't have the same magnitude as this one. This has got greater magnitude. This is the second one refers to a faster tracing, right? The first one refers to a slower tracing. And yet these parameterize the same line. Now, let me try to persuade you that these parameterize the same line. First of all, notice that this is one of those points. Plug in t equals 2. Right? You get that point. Whoops. So that right there, right away, you know that these two lines at least intersect. And knowing that they intersect, and then further knowing, notice that these two vectors point in the same direction. They're parallel. These two lines intersect and are parallel. What does that mean? Right? So they're the same line. Okay. Okay, so don't make the mistake of thinking that there is the parameterization for a line. There's lots of different parameterizations for a line. In fact, there's infinitely many. You can start at any of the infinitely many points on that line, and you can move with any of the infinitely many parallel vectors as your velocity vector. Lots of ways to parameterize a line. Okay. Do notice that I used a different parameterization variable here. Parameter, I guess I should call it, right? I use S just to avoid confusion. People do that sometimes. Okay. All right. Now, so it remains, though, suppose you have a parameterization, sometimes called a parametric line. Fine, right? Technically, the parameterization is the function. The parametric line is the geometric object itself paired with how you've parameterized it. So anyway, so this parameterization, suppose you do want to test points, right? This doesn't do it. That's not a point tester. That's a point generator. So how would I test? Well, there's a simple argument to get you there. Notice the parameterization. I can rewrite one equation at a time. And now let's think through, what does it mean for a point x comma y to get generated? What it means is I plug in a value of t, a single value of t that I plug in. Obviously, it's the same value of t in both equations. And out comes a point x comma y that's on the line. Okay, now let me say that backwards. If a point x comma y is on the line, those values, the x and the y, have to be generated by the same value of t. Let me say that a little bit differently. This value of t, which is easy to solve for, and this value of t, which is easy to solve for, they have to be the same. Right? And now, under what circumstances could this and this both equal to the same thing? Well, they have to equal to each other. And so this right here is an equation for that line in R2. Everybody happy with how that went down? It's pretty straightforward reasoning. So the way you get this, by the way, this is what they call the symmetric equation of the line. I'll tell you why in a moment. I guess you could say it's because the x and the y are participating symmetrically or something. So the process for getting from a parameterization to the symmetric equations is to solve for t, set the results equal to each other. Okay. What if you want to go backwards? Given a symmetric equation, how do you find a parameterization? That's arguably even easier. The things that are equal in your symmetric equation are equal because they're both equal to t. And then just solve for x and y. Okay. So it's an easy process back and forth. There is a three-dimensional version of this. What if you have a line in R3? Well, there's a parameterization of a line in R3. There's that same thing, just written one component at a time. All three of these t's can be solved for. If a point's going to be generated by this parameterization, then these three values of t would all have to equal to each other. And so you get this. We call this the symmetric equations. And there are actually, depending on how you look at it, there's sort of three equations here. Right? There's one equation. There's another equation. And really, that's kind of a third equation in a way. As you can see, the symmetries in the structure of how these are written down. So, symmetric equations. Okay. All right. There's a nice way to interpret these symmetric equations geometrically. I like to show students. I think this is a really nice argument. These three equations. Let's take this one for example. What does that mean? What is this one equation? I mean, there's three equations describing one geometric object. Individually, what do these three equations look like? Well, let's think about it. That thing right there is the equation of, well, let's see here. I could rewrite this thing as, if I did a little bit of algebra, I could rewrite that as something times x plus something times y plus 0 times z, because there's no z's in that equation, right, equals something. I don't know what the a, b, and the d are. Who cares? You can do that. That's algebra 1. That's trivial, right? Some numbers. So this is a plane. What we've got here is three planes. The symmetric equations represent three planes intersecting to give us our line. Everybody on board with that? Next observation. This number here, very conspicuously, is 0. That tells me something really interesting about the normal vector to this plane. The normal vector, which has coordinates a, b, 0, that normal vector to this plane is a horizontal vector. That way, this way, whatever. That depends on the a and the b, whatever, but it's clearly horizontal. And if your normal vector is horizontal, that means your plane is vertical. Everybody happy with that? Another way to think about this, in this equation, z doesn't matter. Right? If you give me an x, a y, and a z, the first thing I'm going to do is I'm just going to throw the z out the window because I don't need that information. That's just taking up space. Right? So z doesn't matter. Now, let's think about that. I mean, what would it mean about a shape in space if you can change the z coordinate and it doesn't matter? Right? Well, that means that your geometric object's got to be parallel to the z-axis. Everybody see that argument? Different way of thinking about it. I think both of these are good. I mean, whether you think about the normal vector argument or the z doesn't matter argument, they're both nice. Yeah?
How'd you get from the blue box to...
Yeah, cross multiply, move terms around. It's just, shifting things around. There's going to be some, you can tell in going from, if I were to cross multiply and move terms around, I'm not going to end up with any x cubes. Right? So they're going to have some x terms, you're going to have some y terms, you can kind of see them. Right? And you're going to have some constant terms. And I'm just going to leave that as, that's just algebra, but it will give you an equation of this form. Yeah. Right. Okay, so what we've got here, this one equation, it represents a plane. It represents a plane that is parallel to the z-axis. And here's another thing. This plane contains the line. Now let me persuade you that this plane contains the line. any point that is on this line satisfies both of these equations, right? If the point's on the line, it definitely satisfies both of those equations. Now, question, how do I know if a point is on this plane? Well, to be on the plane, I only need it to satisfy that one equation. Well, if a point satisfies both of these equations, it's a freebie that it satisfies the first equation. And therefore, anything that's on the line is also on the plane, or said differently, the plane contains the line. Okay. All right. So, So this is the argument I have on the next page here, and so we see that this is a plane that contains the line and is parallel to the z-axis. So it is what I like to call the vertical shadow of that line. Everybody see how that works? And I'm going to leave as an exercise for you guys, and I think this is a really good exercise, right? Really worth your time. Ask yourself, fill in, work by analogy, sure, but try to figure out what is that right there. What does that equation represent? And it's going to be very similar to the argument we just made here. Important differences, that's what you want to make sure to think through, right? But what is that plane? Oh, okay, I just gave you one of the things. Okay, that was easy. And then, what is this? That's something to think through. Okay, so here's a bunch of what I'm going to call related puzzles. Y'all are going to notice this very, very quickly when you get to the exercises for this section. And there's going to be a bunch of questions like this. Hey, here are two lines that go through a given point. Find the equation of the plane that contains both of those lines. Right? So if I were to give you, for example, that line and this line, and by the way, my intention was that these are parametric lines. If I give you two parametric lines, how would you find the color? There we go. How would you find the equation of this plane? Okay, so the general strategy here, as I noted up here, is step one, identify what geometric objects you have or that you can conveniently identify from what you're given. Next thing, identify what geometric things that you need in order to get the thing you're looking for. Right? So the problem is going to be given as, here's some algebra, find me more algebra. Right? Translate that step one into, okay, this algebra I was given. That means I'm given certain geometry, this algebraic thing that I want to find. Okay, that means I want to find certain geometry. Think about it in geometric terms, right? Don't think about it, how to get from algebra to algebra. Convert the given algebra into geometry, get business done in geometry, and then translate back into algebra. Okay. All right, so let's think about this one. How would you do this if you're given two parametric lines? Well, whoops, I didn't want to erase that. Sorry. If you are given this parametric line, then among other things, you know that vector. That's given. Right? And you know that vector. That's given. You can just read that straight off of the parametric line. It's part of the parameterization of the line. By the way, we're also given this point that they go through. Here, I'll be consistent. So that's the stuff you're given. Okay, now let's take a breath before we try to do stuff. Now let's take a pause. I want to find the equation of the plane containing both of these lines. So I want to find the equation of that plane. In order to do that, I'm going to need to find a vector perpendicular to the plane. Right? That's how you find equations of lines. You need that normal vector. And I'm also going to need to find a point in the plane. All right, so I'm given a point in the plane, and I want to find a point in the plane. Right? How am I going to do that? Well, it's obvious. I mean, that's a freebie. It was given, so you already have that. No work required. Okay. the question, right, the big looming question is, how do you find this normal vector? And, whoops. So, how do you find that normal vector? Cross product, right? I want to find this green vector that's perpendicular to the plane. Well, therefore, it's perpendicular to any vector parallel to the plane. Therefore, it's perpendicular to the two given vectors. I want to find a vector perpendicular to two given vectors. Cross product. That's exactly the tool for that job. That makes sense to everybody? Okay. So notice we translated the question into geometry language, and then once I have the question in geometry language, then it sort of comes to this, okay, how do I get, given what I have, how do I get what I want? And it's just geometry games. Okay, here's another one. This is a little bit harder. Given two planes. So suppose you're given the equations of these two planes. Right? How would you go about finding the line of intersection? So again, you got to think, first, so the question presumably would be given algebraically, would be given the equations of the two planes, right? I want to find a parametrization of the line of intersection. So I'm given algebra. I want to find more algebra. Don't want to play that game. Let's instead think about the geometry. If I know the equations of those two planes, I know the normal vectors, right? I may also, well, anyway, certainly I know those two normal vectors. Now, what do I need? I need to find a vector parallel to the line, cross product. Everybody see how that works? By the way, notice how critical this picture is. Right? Please, please, please don't try to think through how to go about this with an algebraic process. I mean, it can be done, but there's just so many different kinds of questions and so many different pitfalls in the algebra that are kind of hard to anticipate in algebra, but that are intuitively staring you in the face in geometry. Right? So please make sure to translate this into geometry problems to actually get work done. Okay, so cross product gives us that vector. Now there is the looming question of, okay, well, yeah, but how do I find this x naught? Right? I may be given a point. Conceivably, I could, maybe deduce some point in that plane and maybe some point in the other plane. But I can't assume just because a point that I found is in one of the planes that it's necessarily in both of the planes. So how do I find that point? Well, again, you have the two equations, and you can just go through and just brute force, just solve the equations. That's like simultaneous equations from middle school. Do you all remember how to do that kind of thing? Yeah. Okay. All right. Okay. This is a really hard one. This, I think, may be a homework question. I never can remember. Yeah, if it. Okay. All right. Good. Someone's reading ahead. All right. What?
There's like a problem that was like.
Couldn't be in 12.2.
You have to find points x, y, z.
Yeah.
That are equidistant to two other points.
Points, but this is different. Yeah. So the question here is given two lines, right? We want to find the equation of the plane.
But then it's the set of all points x, y, z, which define a plane, doesn't it?
I don't remember the question. I'm not sure which question, but it's kind of got to be different because what the question's asking for here is an object that had not been defined in 12.2. So I'll bet there's some similarities, but it can't be the same.
Because the answer also said it was like a plane too.
Okay, that may be. There's got to be something different about that question and this. Anyway, whether this is a question in 12.4, I'm not sure. But yes.
Oh, I just had a question about the one that we just
went over. Oh, okay, sure.
So are you saying that we would make an equation with 1/2 of the plane in it?
I'm sorry, say again?
Would we say the plane is cut in half to get to the line of
intersection? Oh, you're wondering how to find this point right here, the x naught?
Yeah.
No, so that's an old thing from high school algebra called simultaneous equations. If you have, ax plus by plus cz equals d, and ex plus fy plus gz equals h, right? That's the hardest thing from about math is the alphabet, right? Then there's a process that you can go by. Come to my office hours. I'll show you how to do it. But there's an algebraic game that you can play to solve a system of equations. Yeah, right. Yes.
Is V is the cross product of N1 and N2?
Yeah, so I can choose V to be the cross product of N1 and N2. Yeah, so I mean, of course, keep in mind, as we discussed, there's lots of different vectors. This could be any vector parallel to that line, right? All I need is to find any one of them, and I'm going to choose to take the one that comes from the cross product because I can find it. Yeah.
And that makes it parallel to the line. Okay.
Yeah. Exactly. Okay, so this could not be a 12.2. I'll bet you there's strong similarities to a question from 12.2, but it's not the same question. Okay. Yeah. This question can't be answered in 12.2. Yeah. But presumably something similar looking. Okay, so let's do it here. How are we going to find the equation of this plane? Well, so again, let's think about what do we have and what do we want. So, I mean, if I have these two lines, that means I've got a starting point and I've got a parallel vector there. I've got a starting point and a parallel vector there. Those are what I'm given from those two lines. I want to find the plane. Okay, so I'm going to need then some point in that plane, and I'm going to need a vector parallel, perpendicular to that plane. Okay, so now what had been given as an algebra problem, we've got rewritten as a geometry problem. The first part is pretty straightforward. The cross product will give you that normal vector. It's not unlike previous examples we saw. The tricky bit is to figure out how do you get this x naught. How do you find that? And now I'm going to assert that the following formula works, but then I owe you a demonstration that it works. The formula is to take these 2 points and look at their midpoint. Now, seems like a plausible thing to try, right? But how do I know that has the desired characteristic? How do I know that choice? Let me erase this. How do I know that point results in this plane in such a way that distance is equal to that distance? That is not immediately obvious. It seems like a reasonable guess, but it's not immediately obvious. So here's a nice way to do that. Let's compute this distance. The argument is to notice that distance is a component. It's a component of this vector I want to call that vector, I can't call it V, sorry. Let's call that D. It's the component of that vector D in this direction. All right, let's take a pause on that for a moment. The blue distance is the component of the purple vector in the green direction. Is everybody happy with that? So going perpendicular, what I really want to know is, if I were to go perpendicular to the plane from x1, how far is it to the plane? The purple vector says going from the x1 to the plane in some random direction. I don't want to go in some random direction. I want to know the perpendicular distance. So the perpendicular component in component. Everybody happy with that? Okay. All right. Now let's find this right there. That too is a component. It's a component of this exact same vector. That's the same vector because of the fact that x naught is the midpoint in the perpendicular direction. Right? So the light blue distance and the dark blue distance are computed by the same formula, therefore the same value. Therefore, this plane is equidistant between the two lines. Everybody happy? Yep.
I'm confused by the x's being labeled as vectors of the points.
Well, so remember, points and vectors are kind of, there's this relationship between them, right? You can, if you want, you can think of every point in Rn as being represented by its position vector, right? But on the other hand, points are locations. But adding, like if you look, when we write down a parameterization, we talk about x plus v. Well, it's a point plus a vector. What does that mean? Well, it means different ways to think about it, but here's the point. From that point displaced by the vector, that gives you another point. Or you could just translate everything into position vectors and say, well, that position vector plus that vector gives you that position vector. So it's all the same thing. Yeah. Okay, so this is 3 examples of what I like to call, again, these related puzzles. Once you know how to represent things geometrically, geometric things algebraically, and getting from this to that. There's endless ways of forming such questions, and y'all will do a significant number of them on the exercises. Yeah.
So what was the reasoning for the midpoint working to be in the plane?
Yeah, so the point is that the midpoint, this being chosen as the midpoint is what makes those 2 purple vectors, in fact, the same vector. And because these are the same vector, I'm computing the same components, and that makes the light blue distance the same as the dark blue distance. Yeah. Okay. All right, so next section. So we're going to go on to parametric curves. Parametric curves are not that different from parametric lines. They just bend. It's the same idea, though, that you have position as a function of, time. I'm going to say time, but you think of it as time. It doesn't have to be time, but position as a function of a single parameter. Okay. All right. So here's an example. This is a classic first example. Suppose I let x be cosine t and y be sine t. Now that probably rings some bells, right? Flashbacks to trig class, right? So I claim that this is a parametric curve because it gives position, x and y, as functions of one input variable t that I like to think of as time. So position is a function of time. This effectively traces out a curve. Now, what curve does this trace? Well, I think I can persuade you that x squared plus y squared is always 1. Right? Trig identity, everybody remembers that one. So that means that every point that comes out of this parameterization satisfies that equation, which of course you remember from Algebra 2 class is a circle. And then you can persuade yourself by just thinking about, just trace it through. And what happens as t starts at 0 and then, moves along different values of t, you can literally trace out the curve as it moves its way all the way around the circle. So this is a parameterization of the unit circle. Now, everybody good? Okay. Here's an alternative notation. Now, again, you can write the equation sort of, one at a time. Or if you remember that position has x and y coordinates, if position is a function of time, well, let me say that differently. If x and y themselves are individually functions of time, then the entire position is a function of time, and you can just kind of, not think about it as variables that are functions of time, but just think in general, position is a function of time, like so. And so this is a very common way to write it, just x of t. X vector of t is cosine t comma sine t. All right, here's another one. There's a parameterization. You'll note I'm using this notation I was just talking about. So what is this? Well, let's kind of work the other way. If this is x and if this is y, and if I would like to understand what this parameterization is, what does this parameterize? What does this trace out? What I'm looking for is a relationship between that x and that y. And again, you read the x and the y straight off of the parameterization. So can I think of some relationship between x and y? And you can view this as a kind of a, just play around with it until it works. So this x this x, which is 2 plus t, what do you have to do to that? How do you have to manipulate that x to make it look like y? And just play the game. I mean, well, I look at the formula for x, there's a t in it. I look at the formula for y, there's 3t in it. How about I take that x and multiply it by 3, all right? You take that x and multiply it by 3, and all of a sudden it's starting to look a little bit more like y. It's not exactly y, but it does have in common that there's a 3t. My constant's not right. But I can tweak that by a little bit more algebra, just subtract 11 from both sides, right? And now I get 3x minus 11 is, and it becomes wrong color, becomes exactly what y is. And so, as a result of this playing, y is 3x minus 11. And then I say, oh yeah, I remember that. That's the equation of a line. Right? Everybody see how that works? This kind of thing doesn't always give you the result you're hoping for, but sometimes, often, I might even say, this gives you what you're looking for. Okay. By the way, here's another way that you could address that. You could rewrite this as 2 negative 5 plus t times 1, 3. And then from that, you can say, hey, I know what that is. We just talked about that yesterday. That's a parametric line. Right. Okay. All right, here's a harder one. What do you do with this parameterization? Now, you cannot find the equation of this curve because an equation involving 3 variables, by the way, notice 3 variables. That's x, right? That's y, and now that is z. So there are 3 variables involved here. If you have an equation of 3 variables, that'll give you a surface. Right? Well, the example that we've seen of that is the equation of a plane. A plane is a surface. It's not a curve. So don't think in terms of finding an equation here. Here, this is just another tool for your toolbox that works sometimes. Think in terms of breaking it down. What can I say about x and y? X and y by themselves, you can persuade yourself going around in a circle. Oh, we already studied that one. X is cosine t, y is sine t. So in the xy plane, this is going around in a circle. Now that ignores z. When you're ignoring z, you're looking at the shadow, the projection down in the xy plane. Right? But the shadow of this curve in the xy plane is a circle going counterclockwise. Right? And now you can kind of piece it together. Now this is requiring a little bit of 3D visualizing, but here's the idea. I know that this curve that I'm looking at, its shadow is doing this, right? And the z coordinate is slowly rising at a constant rate. Well, you just have to think about what that means 3-dimensionally, and I think you can persuade yourself that it gives you this helix curve. Right? Its shadow is doing this, and it's rising at a constant rate. Yes?
It's like if you have like a slinky on each side.
Yep, totally. Totally, this is a stretched slinky. Okay. All right. There is no sort of single way to figure out what your parametric, if you're given a parameterization, you want to know what does this represent? Sometimes things like this work, sometimes things like we talked about above. There are other tools that I haven't shown you yet that we'll get to later. There is no sort of single, here's how you do it. There's just, here's various tools for your toolbox, and I don't know, depending on what kind of a question you see, pick the appropriate tool from your toolbox, right? And you just have to be able to diagnose and think about what's going to be most useful as it comes up. Okay, what's a derivative? By the way, I think it's worth recognizing that we're finally getting around to talking about calculus. Right? And this is just just barely. We're actually going to do several things after this that are not going to have calculus in them. Calculus doesn't really kick in this class until, third or fourth week. Anyway, so let's talk about this derivative of a parametric curve. Now I'm going to write down this formula because, this is the only formula for derivative that we have, right? This was the formula we used in single variable calculus. And by the way, this is kind of a single variable function in the sense that there is only one input variable. I mean, there's several output variables, X, Y, and Z, so it's different for sure, right? But I don't know, this seems like a plausible thing to write down in the absence of any other better ideas, which will be coming, by the way. So we write down this formula, and that's what does this represent? Now, before I tell you what this represents, I want to urge you, please do not react too quickly and think, I remember from my Calc 1 class that the derivative is the slope of the curve. Everybody remember that? Derivative is the slope of the curve? Not here. Now, why? Is it because this is multivariable and everything's different in multivariable? Not really. The reason that this is not the slope of the curve is because that's not really what the derivative is in Calc 1. In Calc 1, I just want to say it a little bit more precisely, but the devil is in the details here. In Calc 1, the derivative gives you the slope of the graph. Specifically the graph. If you want to interpret derivatives as slopes, it is required that your function, that your function f of x that you're taking a derivative of, you have to be looking at that as a graph. You have to have said, okay, I'm going to take this function f of x. I'm going to choose to set y equal to f of x. Reasonable question at that point is, what's this y you're talking about? I've never heard of y. F is a function of x, end of story. There's no y. You have to choose to make up a new variable to set equal to the output values and then use that as your guidance to draw a specific curve. That's called the graph. And that's a very, very good way to understand single variable functions, and I will give you that. But the fact remains, that is a choice. It's a construction of a particular design, and it is only with that particular choice that you can say that the derivative is equal to the slope. And notice very conspicuously, that's not what we're doing here, right? I'm not taking, my x, in fact, let me write this out. I'm not taking, sort of x, y, z of t. I'm not setting that equal to w or something, and then drawing a how would I even do that? That's 4 variables. I can't draw 4-dimensional pictures. All right? So we're not looking at a graph. So because we're not looking at a graph, we're just looking at the actual output values themselves. We're looking at a picture that is constructed in a fundamentally different way, and so we should assume that the interpretation of the derivative will also be fundamentally different, and it is fundamentally different. So when you're taking the derivative of a parametric curve, this is not a graph, and all of your interpretations are going to change. Okay, all right. So now with that warning having been emphatically made, let's actually figure out what this does mean. There's our point x of t. Here's the nearby point x of t plus h on our parametric curve. The difference vector, let me do that with the pencil. The difference vector, little short vector like that, as h approaches 0, it starts to get really, really short. It starts to become more and more, less and less of a secant vector and more of a tangent vector. But it's getting shorter and shorter. But as I divide by h, which itself is getting smaller and smaller, I hope this brings back memories of Calc 1, that gives it more and more length. Right? And in the limit, what we're going to have is a tangent vector to the curve. So that's our first observation I want to make is the derivative vector is a tangent vector to the curve. Everybody on board? It's not a slope. It's a tangent vector. Okay, next, what is how long is this vector? What's this magnitude here? Okay, well, the magnitude is, I would roughly expect to be the magnitude of the numerator divided by the absolute value of the denominator. And if you think about it, that is distance. That's an elapsed time between the two moments that I'm looking at. I'm looking at the moment when time is t, and then I'm looking later at the moment when time is t plus h. So h is an amount of time. Distance divided by time. That's speed. Right? So what we have here then is this derivative is a vector whose pointing in the direction that we're going and whose magnitude is our speed. Think back to the very first day of class. That's velocity. Everybody on board? Okay. All right. Now, let me go back to Calc 1. Do y'all remember there was a different kind of problem that y'all solved in Calc 1? It was a relatively kind of a side note problem, but you imagine a car is driving along a road, right? And its position is given by, and then they give you some function. And then they ask you to compute the velocity of the car. But if you think about it, that was a parametric curve, right? They didn't draw the graph of the car. The car is not moving up into the atmosphere, right? Position's a function of time. There is no graph. Position as a function of time is a parametric curve. It's a really weird parametric. It's a boring parametric curve that lives inside of the real number line, but it was a parametric curve. And so, in fact, we had already seen in Calc 1 that the derivative was a velocity, and this is just like that. But it's not just like the other interpretation of derivative from Calc 1. Okay. All right. Likewise, by the way, similar argument. Second derivative is acceleration. Let's see. I'm looking at the clock. I got 30 seconds. That will be enough to make this last point. There's a temptation to say, well, I guess you just compute the derivatives one component at a time, but that's not obvious, right? In fact, familiar though this is kind of turning out to be, this is a brand new definition of derivative of a vector-valued function, and it's not obvious that you can just break it down into components. But even though it's not obvious, it is true, and that's very important. But I want you all to see why this is true. This is true because of arguments that we can totally write down. This difference is computed one component at a time. That's how you subtract vectors. This fraction, how do you divide a vector by a fraction or by a scalar? Do that one component at a time, right? We haven't talked about limits yet, but I'm going to ask you to take on faith, and I think this is pretty believable, that the limit of a vector-valued function, you just take the limits one component at a time. And one component at a time, this turns exactly into literally the single variable definition of the derivative of the x-coordinate function, and likewise that's the y derivative, and that's the derivative of z. So good news is derivatives are computed one component at a time, just like you would hope. And I guess that's where I have to stop. We'll pick up here on Friday. See y'all later. Don't forget homework. Oh, I owe y'all an email indicating exactly what sections of the book we've finished, and therefore what is due on the homework. I have to go back to my office and check up and see what we've done, what we haven't done. I'll send that email out today. See you later. Yes?
Where do we usually get homework back?
Oh, yeah, I'm sorry. So at the start of the semester, I did not have a grader yet assigned. I now do have a grader assigned, and he's out of town. So I will, as soon as the grader gets back, he's going to start working on the grading. I'll get the homeworks back to you as soon as I can. Yeah.